we have 10 minutes for the presentation. I will give you 2 minutes more before the Okay, so let's start.
So good morning, everyone. I'm a Form 5 student at Winner from St. Mary's Canossian College. Today, I'm going to talk about the complexity reduction of graphs. So there are many complex networks in our daily life. One example is the brain network. Both structural and functional brain network can be modeled as a graph because nodes and connections are shown. And because of the numerous nodes and connections, we can describe them as the complex graphs. Another example is the flight routes between cities. And this network is indeed a complex graph too. The SOA graph is a geometric representation that can be transformed into an adjacency matrix, which is an algebraic representation. The one in the adjacency matrix means there is connection between the 2 vertices. For example, this one in the first row, second column, means there is a connection between vertex 1 and vertex 2. Whereas the 0 means there is no connection between the 2 vertices. And obviously, AG is a symmetrical matrix, and G and AG is also a 1-1 correspondence. Our idea of graph reduction indeed comes from the idea from the concept of triangulation in topology. For instance, a sphere undergoes triangulation and can be transformed into a tetrahedron. But what we focus on is the triangulation of graphs. A graph embedded in a plane can be divided into phases. For a graph which is embedding a triangulation, each face is bound by a triangle. If some of its inner edges are removed, like this graph on the right-hand side, some loops are obtained. So what do we mean by loops? In a loop, for any vertex, Vi and Vj, they are connected if the difference between I and j is 1, or they are V1 and Vn. We denote n loops as Ln. The below figure are just some examples of loops. So we try to decompose graphs into loops of different orders, which is similar to the Fourier decomposition that decompose the waveform or function into sinusoid of different frequencies. And it is obvious that with fewer edges, the graph is less complex and can obtain more higher order loops. Therefore, we conclude that higher order loops is actually less complex than a lower order loop. So to define the complexity of loops, we did something like triangulation. We add edges to the loop and to obtain more triangles. Because a higher order loop can be decomposed into more triangles, yet it is less complex than when compared with a lower order loop. Therefore, the complexity of a graph is inversely proportional to the number of triangles. A method A we use is to add edges to every vertex to make Ln become a complete graph Kn. So the number of triangles delta Kn obtained will be n choose 3. Whereas for method B, we choose only one vertex and then add edges to it to make it connect to every other vertices. So the number of triangles we obtain will be n minus 2. So we use these 2 symbols to represent the complexity of loops when using method A or method B. And it is obvious that for L3, the complexity is 1 for method A or method B. And it will be also interesting to plot this graph. We can compare the difference between the 2 methods, and then I can show the decrease of the complexity is along with the increase of the order of loops. With the complexity of loops, we can then deduce a formula to compute for the complexity of a graph. So in this formula, we multiply the number of n loops in the graph with the corresponding complexity, and then sum them up for n equals to 3, 4, 5, continue to n. So we have defined that higher order loops is actually less complex when compared to a lower order loop. So what do we mean by the complexity reduction of graphs? Basically, it is to eliminate edges so as to obtain more higher order loops. The procedure is to transform the graph G through an algebraic method into a reducer graph G hat. So the algebraic method we use is to use singular value decomposition to obtain A tilde G, and then perform our approximation and to obtain A hat G, which is an adjacency matrix that can represent a graph G hat. So for any matrix A, it can be written as the product of three matrices, where U and V are orthonormal matrices. UU transpose and VV transpose equals to I. So the sigma is the diagonal matrix, where sigma 1 to sigma r are the singular value of A. So if we, because sigma 1 to sigma r are arranged from large to small, so if we reduce reduce the last few k singular value into 0, we will obtain a new matrix sigma tilde, and thus we can have a new matrix A tilde. However, we do not simply set the last few k singular value to 0 arbitrarily. The matrix A tilde is the best rank n minus k approximation of A, in the sense that the Frobenius norm of the error A minus A tilde is minimized. So let's see an example of SVD. After performing SVD, this A tilde obtained is not an adjacency matrix, obviously. So therefore, further approximation is needed to convert it back to adjacency matrix. So we introduce an approximation algorithm to transfer A tilde to A hat. So the following slide will show the details of the algorithm. However, we will not spend time on them, as most detail has been written on my report. So here is an example. By applying SVD and the above algorithm, we can obtain the we can see the example like this. On the right hand side, the graph G will be reduced to the G hat, and we can also compute the complexity of graph by the previous formula, and reduction is clearly shown. And this one is a complex graph that I compute. After reduction, obviously many edges are removed. So to conclude, based on the idea of triangulation in topology, we decompose a graph into loops in order to measure its complexity. A graph can also be reduced through an algebraic method. We now only consider unweighted graphs. An extension of our graph of our project would be to apply the same method to some weighted graphs. Another possible direction is to relate loop decomposition with Fourier decomposition, as we only mentioned the similarity on the surface. So will there be any deeper interpretation that we can explore? And moreover, the Laplacian graph and the Laplacian matrix is another way to catalyze the graph. So it will be interesting for us to see whether our method of graph reduction can be applied to the Laplacian matrix. So I've just talked about how to reduce complex graph. Yes, I have gone through a complex thinking process so as to obtain only a little idea of graph reduction. So this is the end of my presentation. Thank you.